Every single click you make, every secure message you send, every time you check your bank balance online, it all hinges on this invisible layer of trust.
Absolutely. And that trust isn't, based on goodwill or anything like that. It's pure mathematics.
Specifically, this architecture we call public key infrastructure, or PKI. It's the bedrock.
It really is. PKI is what lets us verify who's who online, keep secret secret, and just make sure the data hasn't been messed with. It's fundamentally what allows secure interactions on the, frankly, untrusted internet.
So that's our mission today. We're going to take a deep dive into PKI. We want to pull out the really essential insights for you on how this trust is actually constructed.
And importantly, where it breaks down in practice, the operational side of things.
Exactly. And then look ahead at what's coming, particularly with quantum computing looming over everything. We'll go from the core math through the protocols securing your browser right now to the real-world failures.
And finally, that quantum cliff everyone's talking about.
Okay, let's unpack this. The fundamental mathematics underpinning modern digital life.
Right, so when we say PKI, we're really starting with asymmetric cryptography, public key encryption.
And the key difference here, compared to older methods maybe people have heard of, like DES.
Yeah, the big leap is that you have two keys, a pair. One key encrypts, a completely different mathematically linked key decrypts.
One public, one private.
Exactly. The public key, you can share with the world, post it on your website, whatever. The private key, you guard that with your life.
And this solves that age-old problem. How do you securely share a secret key in the first place? If I want to send you an encrypted email, I don't need some prior secret channel.
Nope. You just look up my public key. You encrypt the email using that public key.
And because only you have the corresponding private key.
Only I can decrypt it. The security hinges on the fact that computationally, it's practically impossible for someone to figure out my private key just by looking at my public key, at least with today's computers.
Okay, but let's talk practicalities. Encrypting, say, a huge video file. Asymmetric algorithms like RSA, they're notoriously slow, computationally expensive. We don't encrypt the whole 5 gigabytes with RSA, do we?
Oh, absolutely not. That would take forever. This is where the engineer gets clever. It's almost always a hybrid approach.
Hybrid? Meaning what?
Meaning you use the slow, heavy, asymmetric crypto like RSA or maybe elliptic curve cryptography for just one tiny critical job.
Which is?
Encrypting a symmetric key, a key for something much faster, like AES GCM.
Ah, okay. So asymmetric encrypts the key, symmetric encrypts the data.
Precisely. You generate a random, one-time symmetric key, say 256 bits. You encrypt that tiny key with my public key. Then you use that super fast symmetric key to encrypt the actual huge video file.
Best of both worlds. The secure key exchange of asymmetric, the speed of symmetric.
Exactly. Without this hybrid system, TLS handshakes, secure web browsing, it would all just grind to a halt. Performance is critical.
Now, PKI isn't just about keeping secrets. It's also about knowing who you're talking to. Authentication. This involves certificate authorities, CAs, right? These entities that vouch for identities.
Right. CAs are the sort of trusted referees. They issue digital certificates that bind a public key to a specific entity, like a website or an organization. Your browser checks the certificate.
But how do I, as an individual user, prove I am me? Say, when I digitally sign a document.
That's where digital signatures come in, using your private key. When you sign something, you're essentially creating a mathematical proof that only someone possessing your private key could have generated.
And this needs to be robust. You mentioned protocols related to El-Gamal. How does the system ensure I'm proving I know the real private key, power dollars, and not just some related value I might have guessed, powers?
That's a subtle but crucial point. It usually involves signing something fresh and unpredictable, often a shared session key, let's call it dollars, that was just generated perhaps using Diffie-Hellman.
Okay, so I don't sign a static message. I sign this new key dollars.
Exactly. You compute a signature, CPKAG, using your actual private key over that specific dollars. An attacker might try to guess related keys, but they wouldn't be able to produce the valid signature for that specific ephemeral K.
So you're proving control over TIE dollars in that moment without revealing PAL. It's almost like a zero-knowledge proof element?
In a sense, yes. You demonstrate knowledge without disclosing the secret itself.
That's really elegant. And these ideas scale up, right? You mentioned key aggregation for scenarios with many signers.
Yeah, that's becoming really important, especially in things like blockchain or complex identity systems. Imagine needing signatures from, say, 10 different board members to authorize something.
Verifying 10 separate signatures sounds cumbersome.
It is. Key aggregation techniques allow you to mathematically combine the public keys of all those signers, say 1B, C, and so on, into a single aggregated public key.
And the corresponding signatures can also be combined.
That's the idea. You end up with one combined signature that can be verified against the one aggregated public key.
So computationally, it's like checking just one signature instead of 10.
Exactly. It drastically cuts down on the data size and the verification time. Hugely valuable when you need speed and efficiency with many participants.
Okay, so we have ways to encrypt, ways to sign, ways to aggregate. But how does this secure conversation even start? How do two parties agree on a key securely if they don't already share one?
That's the job of key exchange protocols. Diffie-Hellman is the classic. There are others like MQV2.
And the big security win here is something called forward secrecy.
Right, or ephemeral security. The core idea is you generate a brand new temporary session key for every single connection.
Every time I connect to my bank, a new key is born just for that session.
Precisely. And once the session ends, that key is discarded.
The value being, if someone later compromises the bank's long-term private key, or even my own,
They still can't go back and decrypt our past conversation from yesterday. Those session keys are gone. It protects past communications.
that seems incredibly important.
It is. Now, cryptographers will tell you that attacking the math of a well-implemented Diffie-Hellman is, essentially impossible with current tech. But that's different from attacking the implementation.
Ah, the theory versus practice gap again. What kind of implementation issues?
Things like unknown key share attacks. This is where an attacker tries to position themselves in the middle of the key exchange.
A man-in-the-middle attack.
Sort of, but specifically targeting the key agreement protocol itself. They might try to trick Alice into thinking she's agreeing on a key with Bob when she's actually agreeing on one key with the attacker, and Bob is agreeing on a different key also with the attacker.
So the attacker relays messages, decrypting and re-encrypting.
Exactly. The protocol needs safeguards to prevent this. It's the real-world messiness timing, network glitches, coding errors that creates vulnerabilities, often more so than the pure number theory.
Okay, that distinction leads us perfectly into TLS transport layer security, that little padlock icon in your browser. It relies heavily on these asymmetric concepts for the initial handshake.
Absolutely. When your browser connects to a secure website, there's this incredibly rapid negotiation, the TLS handshake. It uses the server's public key certificate to authenticate the server.
And then typically uses something like Diffie-Hellman to establish those ephemeral symmetric keys we just talked about.
Right. And all of this has to happen incredibly fast. We're talking milliseconds.
Which brings us back to performance.
Yeah.
You mentioned the heavy computation involved in asymmetric crypto. How do we make that fast enough?
A lot of it comes down to the underlying mathematical structures used. Cryptographers and hardware designers often prefer working in specific algebraic fields.
The outline mentions Galois fields, specifically GFT dollars versus UFT dollars. Why is GF2 often faster in hardware?
It's all about binary. Computers think in binary. GFT dollars is a finite field where the elements can be represented as polynomials whose coefficients are just 0 or 1. Arithmetic in this field, especially multiplication, can be implemented extremely efficiently using basic logical operations like XOR.
XOR gates are super fast on a chip.
Exactly. And you can use hardware structures called linear feedback shift registers, LFSRs, to perform these calculations very quickly.
What are LFSR simply?
Think of a shift register, a sequence of bits. In an LFSR, the next bit shifted in is calculated as a simple linear function, usually XORs, of some of the previous bits in the register. They're incredibly simple and fast for generating bit sequences needed for these GF2 operations.
And there are specific mathematical choices made here too, like certain polynomials.
Yes, for optimal speed, cryptographers often choose the modulus polynomial carefully. Primitive trinomials, like 6 sounds plus x plus etc. 1, are favorites.
Why trinomials? 3 terms.
Because having just 3 terms with a lot of zero coefficients in between simplifies the modular multiplication process significantly in hardware. It streamlines the algorithms used for things like elliptic curve point multiplication.
So the raw need for speed in that TLS handshake directly influences the choice of abstract mathematical objects.
Absolutely. Engineering constraints shape the cryptographic landscape.
Okay, so the handshake happens fast, we get our symmetric session key. Now we switch to the workhorses, symmetric ciphers.
Right. And these broadly fall into 2 categories, block ciphers and stream ciphers.
Block ciphers like AES process data in fixed chunks, right?
Right.
128 bits at a time for AES.
Correct. While stream ciphers operate on data continuously, maybe byte by byte or even bit by bit.
But the line can be blurry. You can turn a block cipher into a stream cipher.
Oh, easily. And it's done all the time. One very common way is using the counter, or CTR, mode of operation.
How does CTR mode work?
You take your block cipher, like AES.
Yeah.
Instead of encrypting the actual message data directly, you encrypt successive values of a simple counter 1, 2, 3, 4, and so on.
Okay.
The output of encrypting the counter value is a block of pseudo-random bits. You then just XOR that output block with your actual message data block.
Ah, so the block cipher becomes a generator for a stream of key material.
Exactly. It effectively turns the block cipher into a key stream generator, and it's efficient and can often be parallelized.
That sounds robust. But looking back, pure stream ciphers, especially older ones, have had a bit of a checkered history. What's the lesson learned there?
The big lesson, learned the hard way sometimes, is that designs based purely on simple linear structures, like early LFSR-based stream ciphers, can be dangerously vulnerable.
Why linear?
Because linearity is mathematically tractable. If the internal workings are too simple and linear, clever mathematicians can often develop algebraic attacks that break the cipher wide open. We saw this dramatically with WEP, the early Wi-Fi encryption.
Right, WEP used the RC4 stream cipher, and it turned out to be disastrously weak in that context.
Precisely. The way WEP used RC4 exposed weaknesses related to its initialization. So the trend now, even for stream ciphers, is to incorporate design principles more akin to block ciphers, meaning strong nonlinear components. Things like large substitution boxes, or S-boxes.
What does an S-box do?
An S-box is basically a fixed lookup table. It takes a small block of input bits and substitutes it with a different block of output bits, but in a carefully designed, highly nonlinear way.
It scrambles the data based on the key in a complex fashion.
Exactly. It introduces confusion and diffusion, making it much harder to find statistical patterns or mount linear or differential attacks. Good S-boxes are a cornerstone of modern symmetric cipher design.
So even stream ciphers are borrowing these nonlinear block cipher ideas for robustness. You mentioned RC4 and Seal as historically favored stream ciphers.
Yes, RT4 was incredibly popular for its speed and simplicity, though its vulnerabilities, particularly when keys or initialization vectors were reused or weak, became very apparent over time. The FMS attack from 2001 was a major blow, showing how early bytes of the key stream could leak key information.
So the lesson is strong nonlinear design is crucial, but how you use the cipher, the protocol around it, is just as vital.
Absolutely critical. Implementation matters immensely.
And underlying all of this, whether it's generating the private key for RSA or the session key for AES, is the need for randomness. Good keys have to be unpredictable.
Unpredictability, or entropy, is the absolute foundation. If your random numbers aren't truly random, if an attacker can guess or predict your keys, then all the sophisticated math in the world doesn't help you.
Game over before it starts. So where does this essential randomness come from in a computer?
It has to be harvested from the physical world, essentially. Computers collect tiny, unpredictable variations from physical processes.
Like what?
Things like the exact timing of your keystrokes, your mouse movements, fluctuations in CPU temperature, electrical noise in circuits, the precise time it takes for data to arrive over the network, or even hard drive access times. These are sources of physical noise.
And the system gathers this noise.
It gathers this entropy from multiple sources, mixes it together in a process called entropy pooling, and then uses that unpredictable pool to seed a cryptographically secure pseudo-random number generator, a PRNG.
And that PRNG then stretches that initial seed into a long stream of random-looking numbers needed for keys.
Exactly. But the quality of the output depends entirely on the quality and unpredictability of that initial seed from the entropy pool. Weak seed, weak keys, weak security.
This sounds like something application developers should absolutely not try to implement themselves.
Please don't. Seriously.
I know.
It's incredibly hard to get right. You should always rely on the operating system's built-in cryptographic random number generators.
Functions like getrandom on Linux or the crypto APIs on Windows.
Precisely. Use the standard libraries provided by your programming language too, as they usually wrap these OS functions correctly. But even then, be aware of potential quirks.
Like what?
Like, for example, the getrandom call on Linux might have a limit on how many random bytes it returns in one go, maybe 256 bytes. If you need more, say for a large key or initialization vector, you might need to call it multiple times. Good libraries handle this, but it's something to be aware of. Don't skimp on randomness.
Okay, so we've built this picture. Strong math, clever engineering for speed, reliance on true randomness. It sounds pretty robust, yet we constantly hear about breaches. You call this the configuration crisis.
That's exactly what it is. The gap between the theoretical strength of the cryptography and how it's actually deployed and managed in the real world is often enormous. The math isn't usually the problem, it's the human element.
The people setting things up, maintaining them.
Yes, configuration errors, weak passwords, unpatched software, poor management of certificates and keys. The data on this is stark. Some studies suggest something like 97% of data breaches could have been prevented by implementing basic or intermediate security controls.
97%. That's staggering. It implies the attackers aren't usually breaking AES or RSA.
They almost never are. They're exploiting basic configuration mistakes. Default credentials left on a router, a web server misconfigured to expose sensitive files, failure to properly validate certificate chains. It's often embarrassingly simple stuff.
Cyber hygiene, basically.
Exactly. Basic cyber hygiene. One of the single most impactful things, restricting administrative privileges.
How does that help so much?
Think about it. Most users, even administrators, spend most of their time doing routine tasks, browsing, email, documents. If you're logged in with full admin rights constantly,
Any malware you accidentally run, any website exploit?
immediately gets the keys to the kingdom, full system access. But if you operate as a standard unprivileged user for routine tasks, that malware now faces a huge hurdle.
It has to find another way to gain higher privileges. Privilege escalation.
Right. And that's often a much harder, noisier process for the attacker. Research, like studies from the Australian Signals Directorate, suggests that simply doing this using standard user accounts for daily work, along with keeping systems patched, mitigates something like 85% of targeted intrusions.
85% just from those two things. That's incredible.
It forces the attacker to work much harder and increases the chances of them being detected.
And these operational failures aren't just about corporate data loss. They're critical in industrial settings too, right? Smart grid, SCADA system.
Oh, absolutely. The situation in industrial control systems, ICS, or SCADA environments, is often much more precarious. These systems control physical processes, power grids, water treatment plants, manufacturing lines.
And they're different from standard IT networks.
Very different. They often prioritize availability and real-time operation above all else. They might run on very old, unpatched operating systems because upgrading could disrupt the process or hasn't been validated. They often use low bandwidth, sometimes serial networks.
And the protocols themselves, Modbus, DNP3, they weren't built with security in mind.
Not at all. Many of these protocols date back decades, designed for isolated networks where physical access implied trust. They often have zero built-in authentication or encryption.
So if an attacker can just get onto that network segment,
they might be able to send commands directly to controllers, valves, breakers, whatever. An unauthenticated stop command sent via Modbus could shut down a critical process.
how do attackers typically get that initial foothold into these supposedly isolated networks?
Often through exploiting vulnerabilities in the interfaces between the IT network and the operational technology, OT network, or sometimes through a misconfigured device, maybe technician's laptop that connects to both networks, or a poorly secured human-machine interface, HMI, running an old version of Windows.
And once they're in,
They could potentially disrupt physical processes, manipulating sensor readings, interfering with control logic, causing protective relays to malfunction. The consequences can range from service outages to actual physical damage or safety incidents. The lack of inherent authentication in protocols like DNP3 is a huge risk.
Okay, let's switch perspectives. The attacker finds a foothold, maybe as a standard user. They need to escalate privileges. How do they typically do that, exploiting software flaws?
They hunt for vulnerabilities. A classic target is any program that runs with higher privileges than the user who launched it. On Linux Unix, these are often SUID or SGID programs.
Set user ID or set group ID. Can you explain those briefly?
Sure. CYEGI are permission bits you can set on an executable file. If a SUI program owned by root is run by a normal user, the program executes with root privileges, not the user's privileges, for its duration.
Like the password command, which needs root access to change the password file.
Exactly. It's necessary for certain system functions. But if that SUID program has a vulnerability, say, buffer overflow?
Exploiting it gives the attacker code execution as root.
Precisely. Instant privilege escalation. Finding flaws in these privileged programs is a high-value target for attackers.
We hear buffer overflow all the time. What exactly is happening there?
It's a memory corruption vulnerability. Imagine a program allocates a small space in memory, a buffer, to hold some user input, say a username. If the program doesn't carefully check the length of the input,
And the user provides way too much data.
that extra data overflows the allocated buffer and starts overwriting adjacent memory locations.
And what's usually sitting in that adjacent memory?
Often, critical control information for the program, like the return address, which tells the program where to continue executing after a function call finishes. If the attacker can overwrite that return address with the memory location of their own malicious code, which they might have stuffed into the buffer too.
When the function tries to return, it jumps straight into the attacker's code.
Exactly. Hijacked execution flow. Classic buffer overflow exploit.
And what about format string vulnerabilities? Are they related?
They're another type of memory issue, but they work differently. They happen when a program uses functions like print for printing output incorrectly.
How so?
If the program directly passes user-supplied input as the format string argument to print without sanitizing it first, the user can then include special format specifiers like %, or percent, or critically, percent.
What does percent do?
The percent specifier is weird. It doesn't print anything. Instead, it writes the number of bytes already printed by that print file into a memory address provided by the attacker on the stack.
So the attacker can use percent to write arbitrary values to specific memory locations.
Yes. They can carefully craft the input string with other specifiers to control the byte count, and then use %line to overwrite crucial variables, function pointers, or other control data, potentially leading to code execution. It's a more subtle way to corrupt memory.
It sounds like the real root cause of many of these vulnerabilities is insecure software design from the start.
Absolutely. Many security flaws aren't just coding bugs. They stem from deeper issues in how the software was designed, incomplete, missing, or shallow modeling, as the source material puts it.
Like having classes or objects that try to do too much.
Yeah, overly complex entity methods where one piece of code is responsible for managing too many different states or security checks. It becomes impossible to reason about reliably.
So what's a good design principle to counter this? You mentioned immutability.
Immutability is powerful. If certain critical data, once set, cannot be changed, it drastically simplifies security analysis. For instance, a customer ID. Set it once when the customer object is created in the system.
Make it read-only after that.
Exactly. Make it partially immutable. If you need to change it, you have to create a whole new customer record. This prevents entire classes of bugs where state gets corrupted or validation checks are bypassed later. Simple design principles like this can prevent many vulnerabilities before they're even coded. Again, it comes back to that 97% figure. It's often the fundamentals, the configuration, the design, not the advanced crypto, that fails.
We've covered the math, the implementation, the failures. Now we have to look at something potentially even more disruptive, the physics. Quantum computing and its threat to PKI, the quantum cliff.
Yeah, this is the long-term, potentially existential threat to cryptography as we know it, at least to the public key cryptography we rely on today.
Why? What's the core issue?
The security of current mainstream public key systems like RSA and elliptic curve cryptography, ECC, relies on the difficulty of certain mathematical problems for classical computers.
Factoring large numbers for RSA, solving the discrete logarithm problem for Diffie-Hellman in ECC.
Exactly. These problems are believed to be incredibly hard for any conceivable classical computer, but a sufficiently large, fault-tolerant quantum computer could solve them relatively easily.
Using Shor's algorithm?
Precisely. Shor's algorithm, running on a quantum computer, can factor large numbers and compute discrete logarithms exponentially faster than any known classical algorithm. It would break RSA, ECC, Diffie-Hellman, basically the entire foundation of PKI and secure key exchange online.
How do quantum computers get this speed up? What's different?
It boils down to quantum mechanics, superposition, and entanglement. Quantum bits, or qubits, can represent 0, 1, or a combination of both, simultaneously, superposition. This allows a quantum computer to explore a vast number of possibilities in parallel.
And specific quantum algorithms leverage this.
Yes, algorithms like the quantum Fourier transform and phase estimation, which are key components of Shor's algorithm, exploit these quantum properties to find patterns, like the period of a function, which is crucial for factoring.
But building these quantum computers is proving to be incredibly challenging.
Extremely challenging. Qubits are incredibly fragile. They're very sensitive to noise, heat, vibration, stray electromagnetic fields, which can cause errors, decoherence.
So maintaining the quantum state long enough for a complex calculation is hard.
Very hard. That's why fault tolerance is such a huge focus. You need sophisticated quantum error correction codes, which require many physical qubits to represent a single, more stable logical qubit. Building a machine with enough stable logical qubits to run Shor's algorithm on, say, a 2048-bit RSA key is still a massive engineering hurdle.
But the threat is considered credible enough that action is needed now.
Absolutely. We can't wait until someone builds that machine. The migration process away from vulnerable public key algorithms is enormous and takes years, potentially decades.
It's not just a software patch.
Not even close. It means changing algorithms embedded deep in hardware, like TPM chips, firmware, operating systems, network protocols, TLS, SSH, IPsec applications, and crucially, the entire global infrastructure of certificate authorities. It's a monumental undertaking.
The source material uses a pretty strong analogy for the effort required.
Yeah, comparing it implicitly to something like a Manhattan Project for cyber, that gives you a sense of the scale, the resources, the coordination needed at a global level involving governments, industry, and academia.
What makes it so urgent if these machines are still potentially years away?
The capture now, decrypt later scenario.
Explain that.
Adversaries, particularly sophisticated nation-states, are almost certainly recording vast amounts of encrypted internet traffic today. Traffic protected by RSA, ECC, TLS.
Stuff they can't break now.
Right, but they're storing it, hoarding it, with the expectation, or at least the hope, that someday in the future they will have a quantum computer capable of breaking today's encryption.
And then they can retrospectively decrypt all that stored data, government secrets, corporate IP, financial information.
Exactly. So any sensitive data that needs to remain confidential for many years into the future is already at risk today if it's protected only by classical public key crypto.
That really drives home the urgency for critical sectors, government, defense, finance, healthcare.
Absolutely. They need to start migrating to quantum-resistant algorithms now to protect long-term secrets. This involves developing, standardizing, and deploying new cryptographic algorithms.
Post-quantum cryptography, PQC. What kinds of math do these new algorithms rely on?
They're based on different mathematical problems believed to be hard for both classical and quantum computers.
Yeah.
Leading candidates often involve problems from areas like lattice-based cryptography.
Lattices, like grids of points in high-dimensional space.
Kind of. Finding the shortest vector in a complex high-dimensional lattice, for example, seems to be a very hard problem. Other approaches use hash-based signatures, code-based cryptography, or multivariate cryptography. NIST, the U.S. National Institute of Standards and Technology, has been running a major competition to standardize these PQC algorithms.
So the world is actively working on selecting and standardizing the replacements.
Yes. The standardization process is well underway, and the push for migration planning, especially in government and critical infrastructure, is becoming increasingly urgent. It's a global race against a future technological breakthrough. #tagoutro.
So we've really covered a lot of ground. We started with the clever math of public and private keys that makes internet trust possible.
Then we saw how speed requirements shape the actual crypto used, like favoring GF2 math or hybrid encryption schemes in TLS. Yeah. And the absolute necessity of good randomness, good entropy.
But then we hit the reality check, the operational gap. That staggering 97% figure suggesting most breaches aren't crypto failures, but basic configuration errors and hygiene issues.
Especially critical in vulnerable systems like SCADA and industrial controls, where failures can have physical consequences.
And finally, looking ahead, the huge challenge posed by quantum computing, forcing this massive preemptive migration to entirely new types of cryptography.
A migration driven by the need to protect today's secrets from tomorrow's potential code-breaking machines, using things like lattice-based crypto.
So what does this all mean? It means that the security of your morning bank transaction relies on math refined over decades, implemented imperfectly, and potentially doomed by a future computer.
It's a complex stack of dependencies, from pure math down to human process.
Which leads to a final thought. Given that simple, almost mundane failures, poor configuration, admin rights abuse, unpatched systems cause the vast majority, that 97% of real-world damage today, are we, as an industry, perhaps focusing disproportionately on the fascinating physics puzzle of quantum computers while neglecting the urgent need to just fix the broken digital foundations we already have? Do you spend more time worrying about Shor's algorithm than checking basic security settings? Something to think about.